So again, going through that kind of assessment, she found that that particular patient did not have enough peripheral vision. Therefore, the original image, the optic slit, the assessment, and also the peripheral vision assessment. All three together will tell you whether it is glaucomatous or not. So this understanding is really helped us because that helped us to kind of label the images that were given. So all these images, so while it was said yesterday that don't have any emotional attachment, so it was not an emotional attachment, but still we had to work with doctors to understand the domain before we could apply, so this is something similar to the practice school of BITS Pilani, where you learn your theory in the class, but learning theory itself will not really help you because you need to go to practice, you need to go to industry, work with them, see how some of the fundamental principles taught in the classroom actually work out in BITS Pilani, because that gives a lot of insight. So my appeal to the student who are here, if you are due to go for a practice school, make best use of that opportunity. Don't do it for, just for the sake of going and then, trying to get some grade, but trying to get the deeper understanding of how things happen in the industry based on the fundamental principles of so that I thought I would appreciate it. So if you look at these images, so this is a very famous hospital in Hyderabad in southern part of India, which has provided all these images to us. So if you, of course, people like us cannot really make out which is normal and which is glaucomatous, but experts will know. So you see those two images. One is normal, one is glaucomatous, and the kind of image sizes, the images, number of images that we started handling. If you look at normal images, there are 295 of them provided by the LV Prasad. Okay. Now, there are large disc size, medium disc, and small disc. The problem is that depending on where you come from and what your genetic lineage is, people will have different disc sizes. Okay. So some may have a smaller disc. Therefore, it may typically give you a CD or a high value, but then they don't have glaucoma. Okay. Therefore, it is important that all possibilities exist while considering the image database. So normal images are 295, and then within glaucoma, they gave us 120 images, minor one, moderate one, severe one. So we basically had to figure out, based on training and inference, what is happening to the given images. So I want you to understand here, later on my results also are going to show you, the data size, the image size is very small. Okay, so therefore we had to do a lot of augmentation, because when you are working on deep learning, you need to have larger image size numbers so that your training accuracies will improve. So that we did with the help of augmentation. But then the interesting thing about these images is that they are produced under extremely controlled conditions. Okay? So normally if you go to public database, those images are clinical images which typically are not taken in a controlled environment. Okay? So because this was done at the hospital, they could do in a controlled environment, which means that the patients that were considered for clicking these images did not have any other ocular disease. They had only glaucoma. They were not diabetic. They were not hypertensive. So it's under very controlled conditions these images were taken. So therefore, I'm going to show you some interesting conclusion later on, because whatever model we eventually developed, when we try to apply that model to open source databases, which are clinical images, the accuracies were not very high. So which means that you need to really customize your network for a given situation. There is no one size fit all kind of situation that we observe. So these are the public data sets. Acrima, they have large images, Auriga and Christie. So Actima and Origa are large size public data sets, but they are not taken under control condition. That means you walk into a clinic and whoever comes randomly takes images, don't make any other measurement, okay, and show that these are normal or global values. So with that kind of background, where the hospital came to us and wanted to work with us to see how the AI can be applied to fundus images, particularly from point of view of glaucoma, and see how we could help them with the outcome, and which could eventually deployed by the hospital in kind of trying to automate the diagnosis. So it could be kind of a second opinion, like doctor gets a feeling that okay, this could potentially be a glaucoma. But let me also push through the tool and let's see what it says. So the tool by itself is not going to replace the doctor, but perhaps more as a second opinion. So the process, most of you who are working know. So we start with the fundus image, and you extract the region of interest.
5 a.m.
So in the case of glaucoma, the region of interest is your optic component disc. When the optical nerve fiber layer, which is behind the retina, starts getting affected by glaucoma, that is reflected in the way the cup and disc typically get affected. So as I said, the high cup to disc ratio is one feature that characterizes the glaucoma. So after you extract, then, so in this case what you do, because the central region is of great interest to us, we don't really need the peripheral thing. Therefore, we kind of crop it up and then take only the central region. That's what we find here. And then because the data size, the image size is very less. I said 295 versus something like 140 or so. So which means that you need to do augmenting for the training purposes. So therefore we did augmentation both through image processing technology, transformation, splitting, rotating, and that kind of thing. And we also use some of the GAN techniques, generative AI techniques to increase the number. So after that, we applied our deep CNN. So we initially developed our own architecture, but then we found that it's getting complicated. Therefore, we started using the transfer learning models. So I'm going to show you results both with our own CNN as well as the transfer learning model that we used in the process. But then, when you use CNN, there is always this danger of hallucination. So therefore, whatever result that you get, you should be able to understand whether it is true or not, whether the result that you got are correct or not. Therefore, explainable AI comes into picture. So one way that can be seen by trying to visualize what the tool, what kind of features the tool is picking up, and talk to doctor and find out whether it is the same feature they look for when they label an image to be normal or localized. So we use XAI techniques to visualize and try to get the confirmation from the doctor that yes, indeed. If it is not, then you need to conclude that look, it is giving high accuracy, but it's not the accuracy not based on the features typically that characterize the glaucoma, but picking up something else. So all these cases you will see in my presentation. So this is one paper that we published. So you see the third other, Sirisha Senthil, she is a doctor, she is an ophthalmologist, she is a glaucoma specialist in LV Prasad Eye Institute, and she was the one who was advising. So there was a continuous interaction, constant visits from both sides to figure out and to also validate the results. Otherwise, a lot of people say there are a lot of garbage out there in the literature. So you get some results, report high accuracies, okay, the reviewer is very happy with your results and accepts. But who is going to defend? Who is going to validate those results? So that is why involvement with the hospital and the doctor was very important. We spent a lot of time in these interactions. So some of you who are familiar, so you start with input images of certain size. and then you go take them through the convolution layers. The number of layers depends on what you want to do, how you want to go about. In our case, we took 4 layers followed by your fully connected layers, 2 layers, overall 6 layers. And your convolution layer picks up your feature map, then the pooling layer will help you to downsample, and the fully connected layer is going to help you to classify. That's a kind of a process that typically you find in textbooks, and then you also apply maybe in your classroom exercises also. So the table below, the feature extraction, it shows you as it goes through the number of layers. You can see the output shape, keeps downsample, and finally you flatten it out and give it as an input to your fully connected network, and final classification is normal or global at this kind. Now this network, because it's a very early piece of work which we did by ourselves. We didn't really look into what others are doing. We took up, we experimented with, multiple layers, and we found that a 4-layer network was giving a reasonable set of results for us. Then after this, we went to the transfer learning. So as you all know, an existing model, trained model, with the weights already you picked up from that in your dense area, and then you further train the network with your images, set of images, and try to fine-tune those weights to suit your need. That is what we say about the. So transferring the knowledge learned from model from one domain to another. I'm going to show you the model that we use. And obviously, when you don't have access to compute time,